Hi, my name is Ron Lynch. I do web handling training and consulting. This presentation is about web handling mistakes that I've seen and in some cases made myself. After almost 50 years involved with web handling in industry and consulting, I've seen a thing or two. And I must confess, for the first 15 years, I was an untrained hack and did a lot of it myself. This presentation compiles a list of the most common mistakes that people make with webs and equipment. One common piece of equipment is a web guide. Smaller offset pivot guides and steering guides for narrow webs seem to have the most problems. I believe this is because they are small, sometimes installed and maintained on site, and are not hard engineered at the original equipment manufacturer like wide web guides or parent roll side lay guides. The most common mistake I see is the sensor is mounted at the wrong end of the guide's exit span. At this position, the guide's gain must be turned down to prevent overshoot and oscillation. The turn down is done either manually or as part of the consequence of the auto setup function of the guide's control. In some cases, an operator just turns the guide off or puts it in manual to stop the oscillation. However it is done, the result is the same. The guide is slowed or inoperative and the tracking quality is degraded. The farther the sensor is from the roller, the slower the guide reacts. The sensor needs to be as close to the guide's moving exit roller as possible. The reason for this is the guide's moving roller can move the web faster than the web is able to move on its own across the downstream stationary roller. If the sensor is near the moving roller, the web moves with the roller into the correct position, and the sensor sees this right away, stopping the moving roller. When the sensor is near the stationary roller, the moving roller and web reach and overshoot the target position before the web is tracked far enough across the stationary roller to reach the sensor. The control doesn't know that the roller overshot the correct position. The web keeps chasing the overshooting roller and thus travels past the target position. The guide now reverses direction and the chase and overshoot begin in the opposite direction. Short spans are another problem. Offset pivot guides twist the web in the spans approaching and leaving the moving rollers. The web runs straight between the two parallel rollers. Steering guides bend the web in the approaching span and twist it in the exiting span. Both twisting and bending can wrinkle a web if the affected spans are too short. Webs can tolerate twisting better than bending. Webs and offset pivot guides and steering guide exit spans can be as short as 1/2 to 1 times the web's width. The approaching span to a steering guide must be much longer to avoid wrinkles. The approach and exit spans to an offset pivot guide must be at right angles to the plane of the pivot table. Any other angle causes the web to see both twisting and bending at the same time. The combination makes the web more likely to wrinkle, and bending can cause even more mistracking in the web, making it harder or impossible to control. As a side note, you typically see a guide presented in literature and training material shown in the standard orientation. In the field, I've seen installations like this where the designers have gone to great lengths, including installing extra rollers, to achieve just this configuration. There are options. Don't limit the design to just the standard orientation, and don't, if at all possible, add extra rollers to achieve it. See if you can eliminate a roller or two by creatively incorporating the guide into the path. There are options. Get creative. A problem seen with steering guides is insufficient traction on the roller upstream of the guide. When the guide bends the web, the upstream roller must anchor the web to keep the bending from traveling into its upstream span. If it slips on the upstream roller, the bend travels upstream. This is called moment transfer. When this happens, the bend pushes the web more in the mistracked direction. The guide then has to move more to make more correction. This makes more bending traveling upstream. The web moves farther in the wrong direction, the result is the web runs off in the mistrack direction and the guide runs to the limits of its travel in the opposite direction and correction is no longer possible. The bottom line, read the manuals and follow the rules for all types of guides. It is the best way to avoid mistakes with web guides. One could write a chapter on what can go wrong with dancers and accumulators. They're one of the most important systems in a web path, but they are one of the least understood and most neglected. These can be large festoons to support splicing or small dancers to control tension at an unwind or a local process. Poorly or not calibrated systems are common. These take the form of adjustments that have no measurements or poor markings. An example is a weight that can be slid along an arm without any measurement. Another is trying to set 3 psi on a 0 to 100 psi gauge calibrated in 5 psi increments. Other problems are percenter air pressure readings where there is no calibration between the gauge and the tension in the web. Related to poorly calibrated systems are designs where there are large geometry changes as the dancer arm moves. If the angles are changing, the tension is changing, so the calibration is correct at one position only, which may or may not be the normal running positions. None are perfect, but plumb, square, and level seem to be a good design philosophy for dancers and accumulators. Still another form of dancer abuse is altering the system by adding undocumented weights or parts to the system to increase or decrease tension, but without changing set points. I believe this is done because official targets for setup don't work, and people find ways through trial and error how to make the system work. Or maybe the right parts just weren't in stock. Undocumented improvements that don't make it into the official documentation can only cause problems with subsequent machines in production. Binding cylinders, pivots, and slides cause poor tension control and are an indication of rust, dirt, or lack of lubrication. The visual clue is jerky motion of the dancer or accumulator. Some gentle low amplitude up and down oscillation of the system is normal, but jerks or exaggerated swings are an indication of problems. There is money to be made in poorly aligned dancers and accumulators. That is, if you are a consultant. Because of the multiple moving rollers, even small amounts of misalignment between the stationary and moving rollers can cause significant mistracking as the device fills and empties. The misalignment can be well within tolerances to avoid wrinkles, but any alignment error can cause mistracking as the span lengths increase and decrease. Overly large, high-mass moving parts in dancers and accumulators and high-mass idlers can cause tension transients during speed changes and can cause tension problems during splices. Lines can be forced to run at higher tension or to slow down just to avoid breakouts and slack web during splices. On the other hand, too light a design for arms and idlers can result in deflection that leads to wrinkles and mistracking. Components need to be sized to avoid excessive deflection under the forces of tension, but no bigger to avoid mass-related transient problems. Lastly, dancers need a reason to exist, and you need to know what it is. I've seen a dancer in the middle of a web path that controlled rollers that didn't need to be controlled in the first place. The dancer was left over from a previous iteration of the machine. Now it was just a source of process variation. Dancers need to work, they need to control something, and they need to do something useful. Bowed axis rollers are frequently used to remove wrinkles. They are effective at removing wrinkles, and they provide an infinite number of ways to make mistakes. There are other uses than wrinkle removal, and each has its own specific setup to do the intended job. But here I'll just talk about wrinkles. Bow orientation is a common problem. For wrinkle removal, the recommended setup is to have the perpendicular to the direction of the bow bisect the wrap angle. This provides nearly equal paths over the bow, so no position of the web is stretched more or less than others. If the bow is pointed straight into the web, the center of the web is stretched more than the edges and there is no spreading, unless the web is sliding over the bow, in which case it works like a very expensive bow bar or D-bar. Pointing away from the web may cause wrinkles, and pointing upstream will cause wrinkles. You can't have too much money, but you can have too much bow. Not much bow is needed to remove wrinkles. Too much bow can give erratic spreading due to slipping and can cause wear on the roller near the edges of the web. Manufacturers will have recommendations on how much bow is right for all the various applications. Bowed axis rollers are intended to be in full traction. If they are undriven, they need enough tension, wrap angle, and coefficient of friction with the web to maintain traction and drive the roller at web speed. Undriven bowed axis rollers are not good idlers, so they need webs that run at higher tension to be able to drive them. For low tension webs, they generally need to be driven, which brings us to the next bullet point. If the roller must be driven, it needs to be driven at the correct speed. For low tension webs, this means driving it within a few fractions of a percent of the speed of the next driven roller. The problem is the curvature of the shaft makes the drive pulley not square to the rest of the line and variable depending on the bow direction and amount of bow. V-belts or round belts are generally used to allow for the angular misalignment. However, neither of these are good for accurate speed control. This can cause tension problems or allow slipping, neither of which is good for the web or the roller. The approaching span can be too short. Most of the spreading happens in the approaching span, not on the roller. If the span is too short, it limits the spreading potential of the roller, or worse, causes wrinkles in the approaching span. If you add a bowed roller in a desperate attempt to solve a wrinkle problem or on an existing line, span length is more important than convenience. Bowed axis rollers can have the same moment transfer problem that steering guides have. If you are slipping on the upstream roller of the bowed axis roller, you can cause wrinkles to form in the upstream span. Not only must the bowed axis roller be in traction, but the next upstream roller must also be in full traction. When not set up correctly, bowed axis rollers and web guides are examples of correction devices that can cause or magnify problems if they are installed and not managed correctly. The ideal web path, from the web's point of view, is all driven rollers and no idlers, but then the web doesn't have to pay for the drives, at least not directly. Idlers have two uses. They are the low-cost way to make the up and down direction changes in the web, and they are sometimes used as a low-cost backup roller in a process. Idlers eat web tension. The more idlers you have, the higher tension you have to have. Fewer idlers is better. Review every web path before it is built to see if you can eliminate idlers. It saves money and it minimizes idler-related problems. Size does matter. Too heavy an idler causes tension transients during starts, stops, and splices. Too small an idler can have deflection problems and be a wrinkle generator. Idlers and all other types of rollers are generally sized to run in a tension range based on the web they were originally designed for. If you try to run a web and tension outside of the design range, your idlers can be too heavy or too small for the tension you are trying to run. Idlers don't increase tension. People increase tension. More than once I've heard someone say that idlers were added to the path to increase the tension. This is a fallacy. I think the idea comes from pulling a wagon. If you put more stuff in the wagon, you have to pull harder. But that's not the way webs work. Idlers eat tension, and the tension upstream of an idler gets lower. The only way tension can increase after adding idlers is if someone or a load cell turns it up to compensate for the tension lost to the new idlers. If you need more tension, just turn it up. Don't add rollers you don't need. Not all grooved rollers are wrinkle removal rollers. Grooves in rollers can have two functions. In rollers with flexible elastomeric covers, the flats between properly cut and spaced grooves will deflect in an outward direction under pressure from the web, resulting in a wrinkle removing action. The working feature is the outward deflection of the flexible cover. In rigid metal or plastic rollers, there is no deflection and no spreading action. Grooves in rigid rollers are there as tread to allow air to escape from between the web and the roller to increase traction. Knowing the difference can help you pick the right kind of roller to solve a wrinkle problem or an air entrainment problem. Don't underestimate the importance of having driven rollers in the right place and at the right speed. The job of a driven roller is to control the velocity of the web and therefore its strain and tension. If driven rollers don't accurately follow their ramps, don't quickly settle to their target speeds, or oscillate about their targets, there will be tension upsets. On startups, this can delay the production of good product. During splices, it can cause failures. During steady state, it can cause variation in the product. And on shutdowns, it can leave you with poorly tensioned web that can lead to more transients on the following startup. Slipping on driven rollers is the ultimate failure. The roller may be going at the correct speed, but if the web is slipping, it is not. Velocity control is lost. The tension ratio, wrap angle, and coefficient of friction must be such that the web does not slip on the roller during any expected operating condition. So how many driven rollers are needed and where do you put them? In a well-designed web path, driven rollers are distributed along the path to balance idler drag and keep tension within the intended operating range. Too many drives cost money. Too few force you to run tension outside of the design range and closer to the failure limits. You are left with no room for adjustment and can't tolerate normal variation of the web and process. You can calculate the cost of a driven roller, and you may be tempted to save money by skimping. The problem comes from not being able to see the cost of reduced adjustment capability and tolerance to normal variation and limited material grade options in the future. My other presentation at this conference is about developing a new web path and how you can determine how many driven rollers you need and where to put them. I have always used testing and experiment as a way to collect information to prove or disprove a hypothesis, to generate data to calibrate a model, or to gather information to make a decision about something. The common theme to these is a hypothesis, model or question, and a carefully designed test to gather specific data to achieve a defined result. Changes without documentation are not a test. If you turn a knob and something gets better, ask why. What physical properties changed? By how much? How much better did things get? And how are you going to measure and control them? Do machines still have knobs? I don't know. Probably not. So if you enter a new set point and things get better, ask the same questions. These next 2 points go together. When people don't have an understanding of how something is supposed to work, it is hard to troubleshoot. In web handling and just about everything else, troubleshooting is based on knowing how things look or work compared to how they should look or work, and how they measure compared to what they should measure. If you don't have the how they should look or measure part, you're at a loss to know what to measure, fix, or adjust, or that things are even wrong. I said in a test review once, one of the conclusions was that the dancer did not control tension. There was not an awareness that there was a problem with this statement. The person didn't have the should work like knowledge. They ran a test on faulty equipment or didn't know how to measure tension. If people don't understand what they are seeing, they make things up to explain it. Pseudoscience is born. At our level of need, physics is pretty well understood, so there is no need to make up more. A theory without a test and data is just a story, and maybe not even a good story. I've heard some pretty outlandish ones to explain things. If you have a hypothesis, make a prediction and test it. If it works, keep the hypothesis. If not, throw it out. Cost and schedule are why you work on something, but that is not where the solution is. I see companies hire new engineers and assign them to manage quality statistics, downtime, tons per day, to run team meetings, to set priorities, to make budgets, make lists of things to work on. Consequently, they define problems in terms of cost, schedule, and staffing, not in terms of engineering and physical things. These things are obviously important, but you quickly need to turn to observation, hypothesis, testing, and data collection to identify and actually solve a physical problem. But on the job, I often see that engineers don't get the equipment training and management guidance to do that kind of work. Maybe it was an 80s or 90s thing, but it seemed like some expert would write a book and suddenly we had an in-house guru preaching and teaching a new project management technique or product quality methodology or Xerox troubleshooting templates or blue tape on the lunchroom table so we knew where to find the salt and pepper. I don't miss those. I spent my time preaching and teaching web handling. The troubleshooting templates and blue tape are long gone, but web handling is still around. Web handling is not a fad. It is a science rooted in Hooke's stress equals strain times modulus and Newton's F equals ma. You don't need fad managers. You need web handlers that can and want to do it and are enabled and valued by management. Anything less is a mistake. This list could get a lot longer, and I could tell a lot more stories, but that would be my mistake. So just some honorable mentions. Worn roller surfaces are often overlooked as the cause of a problem, as it is the question of why it wore and what to do to fix it. Readouts that are not calibrated in physical units undermine process understanding. Judging parts, processes, or materials by the wrong properties or variables is common. Know what is important to the process and product. Besides the obvious knobs on the control panels, machines can have hundreds of neglected, forgotten measurements and adjustments that determine the quality of the product and reliability of the machine. Don't rely solely on control panel audits and data acquisition systems to tell the whole story. Are there any questions? I hope I'm online to answer them. If not, feel free to contact me at the email shown. Thank you.